Yep.
So this is the development of a visualization technique to see inside a 3D numerical model domain. So for this particular talk here, what I have chosen is to simply show you what results look like and leave the description of the numerical model itself contained in the reference at the end here for those who are interested. So, and again, I want to thank my colleague Steve Albers, who is one of the primary developers of the so-called SWIM model, and Steve Miller. Okay, abstract included for completeness. And so we have here the 3-4 August 2016 Saudi Arabia case. This was funded under the MURI project, where a lot of universities got together and focused on a dust event that occurred where one dust plume was identified and another one was not, and that kind of triggered the whole study of dust detection. And so we have here the RAM simulation with no dust, the GNU dust parameterization, and idealized dust, or Annette Walker's dust parameterizations here. And so this is a top-down scene. This is sort of like a low Earth orbiting satellite looking down. And then going forward, back, I'm just toggling back and forth between different times here. So for example, if you look at the GNU dust, you can see the dust existing over the Persian Gulf, over the Persian Gulf between the two. Here, the Walker dust, you can see some dust there over the Persian Gulf. But the idealized dust was very dusty, and it's pretty obvious as it completely blocks the water bodies below. All right, so this is now an actual, what we're working on is developing the ability to fly through the domain. So what we have here, this is August 3rd. Here's the time. It's changing every 10 minutes. And this is at a constant altitude of 1 kilometer. And we are all scenes, the field of view here is always looking towards the south. And so when I designed all these flights, I flew towards the south because that's the natural thing, is one to look in the direction they're moving. And so you can see cumulus over here to the left, and we're above a dust layer. Okay, and then for the so I actually changed the frames here. So now what I'm doing, if you look at the top right, you see the altitude goes from 1,000 meters, 800, 600, 400, then 200 meters. So I'm actually flying south but descending at the same time. And during that process, you can see some of the land topography starting to show up in through here. So again, these are preliminary tests of simulated flights. Here's the direction. This is due south. If you look off to the right a little bit, that's due west. To the left is due east. So this is actually a 360-degree cylindrical view on August the 3rd. Okay, so I guess we can spend a little more time on the next case here, 17 September 2019 in the Philippines. There was a pretty large field campaign with boats and planes in and around the Philippines looking at aerosols, observed aerosols. And so step number one was to first run RAMs and simulate that particular region. So this again is sort of, actually this is a simulated VIIRS image. We set the point of view around, I think it's 800 kilometers above the surface, which is consistent with the VIIRS satellite. So in here, the blue is the water, green is the land mass, and then the white are the clouds here. So this is like a true color image of this particular case. So what I did is I set up some flights going from north to south moving just along the coast in the southeast Philippines, and I also did a flight going north to south in through a cloudier region. And so here is the RAM's topography. The values here shaded are in meters, and so you can see it's very mountainous, and through here you go from near sea level up to 3 kilometers above the sea surface here. So, and same thing down here, there's lots of complex terrain in through here. So what I'm showing here is flight number 1. We have 2 latitude belts, latitude 6 degrees, latitude 8 degrees, and then longitude of 126.5. And then where these two intersect, I start the flight here at 8 degrees north and fly south to 6 degrees. So you will see the landmass show up on the right here. So again, we're looking south. We're at 1,000 meters above the ground, and we'll just let this loop every 30 seconds. You can see and also I want to point out that the meteorology is changing in the simulated domain. So as opposed to keeping the meteorology fixed and just flying south, that is also varying with time. Okay, and so one of the primary goals here is to be able to have dust or some aerosol in the simulation along the coastlines, so when one is flying, one would be able to see the difference between more of a maritime atmosphere as opposed to one where there is aerosol along the coast. Okay. And then you can see the anvil extending off from that cumulus as we almost complete our flight here. So we had moved south of the Philippines and back over into the open water. Okay, this is about to finish up here. It was just a 30-minute simulation, and then it's going to begin again. So we'll let this go through one more time so you can orientate yourself here. Cumulus over the landmass. We're flying due south, going over the land. We're actually was trying to fly right along the coastline here. All right. Again, we're flying at constant altitude of 1 kilometer going due south. And just as a reminder, this is actually 360 degree perspective here. Okay, so now we've left the landmass and we're heading due south over the open ocean, and this has a few more minutes. I guess while this is looping, anybody feel free to ask a question while we watch this looping here. There is another loop coming up here. And I'm hoping that I set the frame rate slow enough so that the rate at which I'm seeing it loop on my screen is identical to what you see. All right, so now I will move to the next flight. So this is in the northern Philippines, starting at 19 north, flying to 17 north, and a little further to the west, 121.7. So the flight begins here and then extends southward. Okay, and so as you remember, actually I'll go back a few. So you can see we're flying in through here, so there's considerably more cloudiness. So we are heading due south, and what I tried to do was fly right in between these mountain ridges off to the east and off to the west. I did a couple of these flights, and it turned out it was just cloudy enough that the landmass was kind of hard to actually see. So what you can see, we're flying through precipitation, flying through clouds, and then coming into like a clearing. You can see the glow of the sun up here, and during this simulation, the sun actually does migrate off to the west. You can see towering cumulus. Now we're over land, kind of in a valley in between ridges to the east and to the west, but there's, again, plenty of clouds. So this technique does offer a unique way to look at a numerical simulation as opposed to the standard top-down or horizontal cross-sections, things like that. Okay, this is getting near that had ended, so we'll go through this one more time. Again, this is a 360-degree view. We're flying at 1 kilometer. We're over the open ocean right now. This is sort of the reflection of the sun off of the water, the diffuse sun here. And we're headed right into that cumulus, and we'll pass through it, back over the open water, and then into a valley where you can see we're heading into cloudiness yet again. Okay, we're about halfway through the simulation. We're right into a valley. And it looks like the clouds are actually moving to the left, but actually it's rotating because of our 360-degree field of view here. Right, we're almost coming up to the end of this particular simulation. Oh, I think this started again. Sorry, I missed that. All right, so I will move on. This is a reference, and while we're sitting here at the reference that describes details of this particular simulation, I can give you a little bit more description of how this technique is done. So RAMS was run, and then RAMS data has to be processed first. You can't just, this model, the SWIM model doesn't just read in RAMS data. So the SWIM model has its own vertical grid, and so you have to take RAMS output, and in particular the microphysics. There are 8 different microphysical species in RAMS, and you have to interpolate them to the SWIM vertical grid levels. Also, there's issues with the topography, because you want to make sure that when you fly, you don't, fly into a ridge or anything like that. So this was what we're looking at here is preliminary work. It's under a lot of development. And again, the goal is to help to try to understand or visualize aerosols, what they look like in a numerical model, as opposed to just like looking top down or taking vertical cross sections and trying to visualize what things look like. In addition, this is also time variant. So with typical horizontal cross sections or vertical cross section, it's usually at a specific time. So with that, I will end again, and thank you very much.
Thank you. Thank you very much, Louie, for very interesting talk. Does someone have any questions or comments? Nobody has questions or comments. Louie, I have a question. I have some questions. If this visualization system is computationally heavy?
Extremely, yeah. Thank you for bringing that up. Yeah, this is, okay, so I guess we got to get into the physics a little bit, right? So this is like does a lot of three-dimensional ray tracing of photons. And this, any one of those flights that you saw in the Philippines took, so that was a half an hour flight every 30 seconds. It took like 8 hours of real time to run swim to actually produce those images. So it's kind of one of these things where you start the model just before you go home, and when you come back the next day, it is done. However, you know, my whole background for 30 years has been running numerical models, and I'm very used to starting a model and, you know, come back in a couple days and see how it's going. So this actually 8 hours to me is, you know, relatively not very long as far as running numerical models is concerned. But yeah, it is time intensive. I don't want people to get the impression that, you know, you hit enter and, you know, you wait a minute or two and it's done. It's more like 8 hours and it's done.
For what kind of operational purposes or operational systems are you going to use this visualization system?
I think the word operational is way ahead of where we currently are. So the goal is to first develop this tool further. And the next step would be more of research, not necessarily operational. And the research component would be to actually include dust, for example, in the RAM simulation, or aerosol. You know, for example, in the Philippines, it's not going to be dust. It would be more like smoke, for example, biomass burning or other kinds of wildland combustion. So to have the ability to get that aerosol into RAMs and then visualize, you know, in that experiment, there are actual flights that took place in and around the Philippines, and they had a camera. So you could see what, you know, visualize, you were able to see what the plane saw. And so the goal here is to use that as observational truth. And while we're developing the swim model, include the aerosol and RAMs, and then run swim on the RAMs output and be able to visualize the aerosol along a flight, and then ask the question, does the observed flight, that view, support the results of swim? In other words, does the aerosol in the numerical model, is it supported by observations? Once that happens, then, you know, you have a stable system, and then a conversation about operational transition or anything like that could begin.
Thank you. Does anyone have further questions or comments? If no, time is almost